So hello everybody. Thank you for joining us today in our webinar about understanding the cure behavior in rheology kinetics. My name is Elena and I will be your host for today's webinar. And before we start, just a few remarks. So if you have any questions throughout the webinar, please type them in the question box below. At the end of the presentation, we will do our best to answer as many of these as possible. But if we do not get to your question, don't worry. Adrian and Elena, our presenters today, will answer your questions afterwards in emails. Furthermore, the recording of the talk will automatically be sent to you within the next few days. So before we really get started, I would like to introduce you to today's speakers, Dr. Adrian Hill and Dr. Elena Moukhina. Adrian is one of our product technical specialists for rheology at NETZSCH, and he's based in the UK and has gained over 15 years of experience in the field of rheology. And he supports our customers in getting the most out of their measurements in both rotational and capillary rheometry. And Elena has been a physicist at NETZSCH, analyzing and testing for the last 18 years. She's based in our headquarters in Selb in Germany and has been a huge contribution to the development of the Kinexus Neo software, which she will demonstrate today. So I hand over to you, Elena and Adrian. Let's get started.
Cool. Yeah, thank you very much, Anna. And yeah, thank you all for attending today. As introduced, my name's Adrian and I'm one of the rheologists here at NETZSCH. Basically here, my job is to help our users, our rheometer users on how to get the most out of their instruments. And that in part is what we're going to be doing today. But what we're going to do is slightly different in the fact that we're looking at how we can couple together, we'll say, practical rheology measurements to look at the curing kinetics, but then take it one big step forward, as in using this data, putting it into kinetic modeling software, our Kinetics Neo software, to then understand, really in more detail, instead of just measuring just under a few conditions, and each of those conditions on a rheometer, they'll take time, as we'll see. The advantage of modeling software is then, the limit is tends to be your imagination. How do you want to set the conditions? You can model them. You can then, with a few mouse clicks, then understand how the material will behave. So that's going to be the theme. That's what we're going to be doing. We're going to be looking at how we can use our different techniques, our different technologies together for you to get the most out of your, material understanding. So the presentation today, we split it up into three main parts. I'll kick off with the first part, which is introducing rheology, looking at some of the terms, looking to see at what type of measurements and how we do them with our Kinexus rheometer. Then my colleague Elena will then take on introducing kinetics, looking about and bringing you on board with Kinetics Neo, our kinetic modeling software, to then saying, okay, what's the theory? How does it work? And more, what do those results mean when you do input this data into this system? And then to try and tie these two parts together, okay, let's give a case study. So what we'll do is we'll look at a relatively common epoxy curing system. We'll make a few measurements on the rheometer, but then we'll take that very same data, add in extra data, for example, from a DSC, and then look how that modeling can then give us a lot more understanding of the various types of material behavior predicting under different conditions. So really a fuller picture of what's going on. So without further ado, let's kick on and look to get understanding of, how does a rheometer measure rheology? What does it give us? What are the parameters that we're interested in? So just very quickly in this first part, we're going to go through, let's introduce rheology, okay, and let's talk about it as the material science measurement, the direct measurement of the material changes. And then look at that in context of, the theme of today, the theme of now, looking at the curing process. And as part of that, as we go through the terms, we'll look at that in practice in typical cure profiles. What do we look for and why? Why is this important to our materials? So to start off with, right at the beginning, what is rheology? Okay, quite often what we have to do is we have to talk about rheology as in saying, it's more than just viscosity. And that's a good place to start. Rheology, we will discuss viscosity. But really, it's nice to think of rheology as, the definition is a good place to start. The science of deformation and flow. What that means is it is a material science. It's a material properties that we will measure. But what we need to do, and what's going to be important for this session today, is put it into context. We need to simulate the conditions the material will see. But what we also see and what we'll also talk about is how it's more than just viscosity. Curing, for example, classic. Okay, yes, by all means, we start off with a viscosity. We start off with a liquid-like material. And if you like, we can even consider some simple epoxy systems starting off as simple Newtonian flow, the simplest flow behavior there is, which is what the video in the bottom right-hand corner is showing you, how we can have reversible flow with a very simple material. But then as materials cure, as they gel, you're going to get more structure. You're going to get more rheology. And that's the idea of the picture on the left-hand side, showing just how stiff the material can get, how solid-like, and especially with curing, of course, that's going to be massively, massively stiff. So what we'll do is we'll put this together. We'll put this into context of a curing reaction. Okay, let's get these numbers to understand how the material behaves. So of course, to measure rheology, what you need is a rheometer. And yes, we say the science of deformation and flow, but for curing, very much the primary measurement choice is oscillation testing, looking at this deformation. So instead of flowing the material, what we tend to do is we look at this oscillation, oscillating back and forth on the material, okay? So effectively what we'll do, and we'll come to see in more detail, we apply a sinusoidal signal to the material, just twisting it back and forth. But what's important to remember under this, remember mimicking the conditions that materials see? This is a non-destructive test. What we're doing is looking at the material, well, before it flows. So for curing, let's look at it under the static environment. And that's a good place to start in terms of a rule of thumb for oscillation. If you can see the rheometer moving in oscillation, you're doing the test wrong. We're looking really at the material at rest. So we oscillate, we twist, we go back and forth. And effectively what we're doing is that we're applying a force, a stress, and then measuring the resultant movement, the strain. And the idea is what we get to do is we get to measure a few different material properties. Depending on your analysis preference, some people might like the complex modulus, others the phase angle, tan delta, maybe even looking at the Cox-Merckx rule to get the complex of dynamic viscosity, or even G prime and G double prime. So how do we go about getting these material properties? So what we need to do is, of course, we need our rheometer. We need to get this thin slip, the thin sandwich of material between our upper moving geometry and our lower temperature controlled plate. But one of the big practical challenges, of course, is, well, we're looking at curing materials. Curing materials, well, a lot of the time they are designed to literally stick materials together, well, as hard as you can stick materials together. And one of the first practical considerations is the fact that we don't want to stick our instrument together forevermore, okay? So what we do typically with curing systems is we have these accessories. In this case, we're looking at the disposable plate system, which means for just a few euros for a pair of measurements, a few euros means that we can do one measurement of one material, cure it as much as we like, and then we can just dispose of it, take seconds, and then really unload it again. But this is also a nice way to start introducing some of the advantages that we have with our Kinexus rheometer, in that, yes, rheometers are very flexible pieces of kit. They've got multi-modes of operation. That's what they're designed to do. So we can do tack testing, for example, these days. But to do that, what we want to do with our Kinexus is make our focus on the results. Well, that's the theme of this webinar today. Let's look at the results. What does that mean for our material? And here we see an example of, okay, there we've got our disposable plates. But we also see with the software how it actually guides our users through step by step how to use these systems. And that's the idea. Let's focus on the results rather than worrying about how to encourage the rheometer to do what we want to do. So we have our rheometer, we have our disposable plate systems, we have our sample, we're looking at the cure. And yep, let's skip right to the end, if you like, with the results. We'll come back and look at how these are made up in the next few slides. But this is why we do it. What we want to look at is the profile. The profile be on the x-axis against time or temperature profile with time, even things like light radiation, UV radiation to kick off the free radical reaction to start a cure. That's what we can do, okay? But at the time, we always tend to look for the same sort of trends, which is what we see here. So what we can see here is that we're looking at the change in the material as it's curing. So if we look at the light blue, the dark blue and the red line, effectively what we have here is the change in, we'll say the modulus, the change in the complex viscosity. And what we can see is a general trend. Let's keep this quite general for now. We start with the material relatively soft and go through to a material which is pretty stiff. So we start low, go high. Yeah, great. That's what we expect. That's what we know of a curing material. But then if we start to look in detail, we start to look at, well, we'll introduce it in more detail next time, the phase angle. We see that the phase angle, this is now the green line, we start to see that, well, the change is opposite. Why is this? Well, the phase angle tells us about the fluidity of the material. The material will start off being a liquid, okay? Doesn't matter about the viscosity, that's not what phase angle tells us. A high phase angle tells us that the material is very fluid, and it stays fluid over a few minutes, but then there's a rapid change as the material gets structured, and then after a while there's a continuous change in the material as it gets more and more solid. And that's what we want to get. That's what we want to get in rheology. We want to see this huge change in modulus. You know, we're talking here about 6, 7, sometimes 8 orders of magnitude change in the viscosity, the stiffness of the material, and then how the material changes completely from a liquid with a high phase angle through to a solid. So, okay, that's what we want to do. So where do we get this from? Well, let's go into a bit more detail about these terms. So in the first place, if you like one of the more simpler terms to appreciate, the complex modulus. Or really, I should say the complex shear modulus, because we're applying a shear deformation to the material. And effectively what we do is we have our lower temperature controlled lower plate. We have our thin sandwich or thin layer of material sandwiched between then our rotating top plate. So effectively we rotate the top plate a little bit back and forth, because what we do is we then look at measuring the modulus. So effectively we twist the material, we twist it with a given force, the stress. We can then measure the given displacement, the strain, and then the ratio of the stress over the strain is our modulus, our stiffness of the material, if you like. And of course, these days the software does the calculations for us. So that's what we want to see. We want to see the material start from a low modulus to a high modulus. That's our cure. That can be our gel. But we can also present the data in other ways. And one of the ways, a more common way, is to look at, we'll say, the complex viscosity, the dynamic viscosity. And this is using an approximation. Okay, yes, it's an approximation, even though it's called the rule, the Cox-Merckx rule, which says that within an oscillation, well, we can basically predict, or we can approximate what the viscosity would be in the material. Half the time, yes, viscosity, those are values, numbers that we're could be a little bit more appreciative of. But really for this and this webinar, all we need to know is that the modulus, the viscosity, or the complex viscosity, the dynamic viscosity, they're all going to show the same trends. In fact, it's just a small scaling factor, Cox-Merckx, based on the angular frequency to get them well, recalculated. Okay. So the idea is modulus, viscosity. We're going to go from a low modulus, a low viscosity material, Maybe we'll have local minimas all the way up to a very stiff material. So yeah, curing, of course, we're going to go from a weak material to a stiff one. But rheology, what we can do is look into more detail. That's the stiffness of the material. There's going to be phase changes as well in the material. And this is where the phase angle comes in. The phase angle, this is now a measurement, a direct measurement of, oh, shall we say, the fluidity of the material. If we have a phase angle which is 0, and by 0, what we mean is the phase lag between this oscillating signal that we apply and the resultant material property, the material's response. If there is a 0 phase lag, which is how a solid, a purely elastic material behaves, therefore we can say the material is behaving like an elastic solid. So what that means is for a solid, if we push and we pull on it in an oscillation, it responds instantly. So phase angle is 0. The other end of the spectrum, this phase angle spectrum, this fluidity scale, shall we say, is for a viscous material, one that now is giving a liquid-like property. Liquids flow. All right, there's no big surprise there. You know, we all know liquids flow. That's what makes a liquid. But to flow takes time. So what does that mean? Well, that means we measure a phase lag between the deformation we apply to the material and its result. So we get a measurable phase angle, a phase lag between the applied and the resultant signal. So you can do this yourself. You can think about putting your hand inside a fish tank and dragging it forward and back. As you push it one way, you feel the resistance to flow. All right, that's viscosity. But then when you pull your hand back, you can still feel the flow in one direction before it comes back the other way. Liquids flow. To flow takes time. This time is a phase lag, which we will measure with the rheometer. The software does it automatically for us, which is called the phase angle. So what we need to take away from this is that the phase angle is, well, we call it a scale of fluidity, from anywhere from 0, completely solid, all the way to 90 to be completely liquid-like, okay? Some people, especially if you're focusing more on the solid side, for example, DMA, dynamic mechanical analysis measurements, tend to be a bit more familiar with tan delta. Yeah, no problem. It's another parameter that's calculated automatically in the software. Tan delta is literally the tangent of the phase angle. Effectively, it's just a way of scaling from 0 to 90, instead 0 to now infinity, okay? And anywhere in between. But that's what the phase angle gives us, this indication of whether or not the material is elastic, solid-like, or viscous. What we can also do is we can take this modulus, we can take this phase angle, and then we can split up the modulus depending on the size of the phase angle, which is where you may come across G prime or G double prime. The viscous, the loss modulus, or the elastic, the storage modulus, G prime. Okay, yes, we can go into details, you can go into the mathematical analysis, but for the need today, all we keep it is relatively simple. And let's consider a straightforward glue, right? You know, a straightforward glue that's going to start with the liquids because we need to apply it, we need to put it where we want it. Then of course we want it to be a solid now to stick. So what G prime and G double prime tells us is, yes, together we can see how the stiffness of the material increases over time, but it also tells us how it goes from a viscously dominated material at the beginning, because G double prime, this liquid-like modulus dominates at the beginning, through to a G prime dominated material, a material which is elastic as we go on through. So from more liquid dominated to new solid dominated, which is then where we can define things like the gel point, where the material is just as much viscous as it is elastic, okay? So all of those are available inside the software. They're all calculated for us. Different people have different preferences. Myself, I tend to like to go back to what the rheometer measures, modulus phase angle, but certainly, you know, we will look at G prime, G double prime, complex modulus or complex viscosity and the dynamic viscosity as well. And that's where we see with the rheology measurements. That's where we're looking at the overall view. All right, if I just go back to looking at these cure examples. So what we can do is in this example, we're looking at G prime and G double prime. G prime, the elastic modulus starting off in red. G double prime starts off, well, it's in blue. And as we start the measurement, we can see that the material is viscously dominated. Then as we go through the cure, yes, the moduli, both of them together are both increasing until we'll switch over, because the material goes from being viscously dominated at the beginning to now elastically dominated at the end. So another way of looking at this and another way of considering this is you can now look at the phase angle. So now the phase angle, this is plotted in green, and what we can see is now we have the trend and you can see bigger transitions. So of course the material starts off being viscously dominated, so we have a high phase angle, liquid-like. And then for one material, the one with circles, you can see that the phase angle slowly decreases all the way through. Whereas on alternative curing system, well, okay, they start off quite similar up until about a similar time. Maybe this is with a temperature profile. But then now the sample in squares, there's a rapid change. The material really just changed very significantly from a free-flowing fluid material, where the phase angle's high, through to a material where, well, it's got a lower phase angle, it's now more solid-like, it's not gonna want to flow as much. So that's the idea with rheology. What we can do is look into detail about how the material changes as we cure through the measurement. So what we do is we can do a measurement, we can look at the material, but really consider these times. You know, this is a cure material, 9,000 seconds. So what we're talking about, you know, approaching here now, like 3 hours. These are significant. So what happens if we can do a little bit more with this? What happens if we can model this? And that's what the next section is about. And this is where I hand over to my colleague, Elena, where she now introduces Kinetics Neo. Okay, thank you, yeah. Elena.
Yes, thank you, Adrian. And now I would like to tell you about kinetic analysis of rheological data. And a first point is what is the kinetic analysis and what is Kinetics Neo. So it is a short introduction. It shows what is the chemical kinetics, and it will be some example, very, very simple example of curing data with live presentation with a software. Firstly, if we have some chemical reactions, for example, curing, then we have two materials. First is uncured material, it's A here, is a reactant, and the second is a cured material. Here it's B, it's product. And we have some reaction rate from A to B, which depends on temperature, concentrations, and other parameters. And if we speak about a reaction rate, then we have a chemical kinetic, which can answer the question, how fast is this reaction rate? What is the reaction mechanism? And how to describe reaction mechanism mathematically. We use Kinetics Neo software to answer of all these questions. Just a very, very simple example from another field, from ceramics, how Kinetics Neo can help our customers. For example, for ceramics, during production of ceramics, we need some firing of ceramics. And the question, what is the optimal firing profile? Usually, in order to find this optimal profile, the people use try and error method, and it is very long, very expensive, because each firing could be about 1 week or just several days. And especially important, it's for new materials. For example, our customers, Morgan Advanced Material, has a new, very, very nice material with very nice properties. It's ceramic foam, and they have a problem. If the curing is too fast, then there are some cracks, deformation, and destroying of a structure of material. If it's too slow, then it's too expensive. Yeah, we speak about sintering. They come to us and say, could you please make optimization of our temperature profile, because it's too expensive to do it by try and error. We just take our laboratory measurement very fast. we make kinetic analysis of this measurement and simulate the optimal temperature profile. We have reduced the total firing time, sintering time more than twice, and we improve the quality. Our customers were really happy because everything was really very fun and fast. Now, if we speak about curing, how our kinetic can help during curing and cross-linking. Here we speak about paints, about adhesives, about epoxy resin. Main questions: what happens during curing, at which temperature reactions start and finished, temperature and time, what is the optimal process, how high is degree of curing and glass transition temperature at the end of the curing, how to reduce curing costs during production, and what is the final state. Is it already glass, or is it still elastic solid or viscous liquid? In order to answer of this question, we use our kinetic analysis. How it works? Firstly, we have some data from laboratory where the measurements are done at different conditions. For example, different heating rates or different isothermal temperatures. Then we take this data and go to our software. We make data import and processing. For example, smoothing of data, selecting the evaluation rate, remove the baseline. Then the key point, kinetic modeling. We can create a kinetic modeling, one kinetic model, mathematical model, which can describe all our measurements. So one model can describe several measurements which are done at different temperature conditions. So, and if our model, for example, autocatalytical model or model of Kamal-Suror equation, Friedman-Asava model, doesn't matter. If our model can describe behavior of our curing system at different temperature conditions, then we can take this model and make a simulation for new temperature conditions, for user-defined temperature conditions. For example, for different isothermal conditions, for different dynamic conditions, different heating rate or complex temperature program. We can predict degree of cure. We can predict reaction rate or curing rate. We can predict viscosity value. We can make some kind of optimization of conversion rate and curing profile. Here in rheometry, we have our instrument, for example, Kinexus. We make some rotating oscillation of the upper plate. The lower plate is stable, and we have a sample between it. We make some kind of curing, heating, or just wait some time, and we have some curing reaction, for example, like in glue or like in paint. What we can measure? Here we have 3 curves, but in reality we measure a little bit more. And the curves like storage modules and viscous modules, they have some step, some increase. During this increase or in these curves, we have some chemical reaction, and the material becomes to be more viscous and then more stiff because of the curing. Initially, it's liquid, and at the end, it's solid or like glass. And tangents delta show our glass transition position and some other additional things. For example, if you speak about viscosity, shear viscosity, then the shear viscosity contains of 2 parts. First of them shows how the viscosity depends on temperature without any chemical reaction. For low temperatures, we have hard material. Material is hard, viscosity is high. For high temperature, material is soft, viscosity is low. So it's just normal behavior, normal temperature dependence of viscosity without any chemical reaction. And now we have chemical reaction, curing. Originally, the molecules or chains are small and we have a high mobility and we have low viscosity, then we have during curing some chemical bonds inside our material, and viscosity, we have viscosity change and like a step with increasing of viscosity. And finally, a measured data looks like this, decreasing because of just normal viscosity dependence on temperature, then increasing because of curing reaction, and then decreasing because of temperature dependence again. And now what happens, if we make some kinetic analysis. Firstly, we have our data. Here we have measurement with 1, 5, and 2K per minute. Then we can make some pre-processing. We can make some smoothing. We can remove a slope, which is not important for curing, and recalculate it everything from 0 to 1 and have a second picture, which called conversion or degree of cure. Here, conversion change or degree of cure change from 0 to 1. Now we have information only about curing. All other non-necessary information is removed. Now we take this in this course and we can describe them with mathematical equations. So we use these curves for mathematical modeling. Here we have a mathematical equation for describing of all experimental curve, one equation for all curves. Here is Arrhenius equation. Alpha is degree of conversion, and in the curing situation, in the curing case, it's degree of cure. A is pre-exponential factor. F of A is a current reaction type. E is activation energy, and T is temperature. So this Arrhenius equation shows us what is a reaction rate at the current state with the current temperature. If the temperature is different, then the reaction rate is different. If you speak about curing, then usually reaction type is autocatalytical type. Here we have two additional parameters. A first one is order of reaction, a second one is order of autocatalysis, and pre-exponential factor for autocatalysis. How to find them? Very easy. A software can just find all these unknown parameters to make a best fit between this simulated data for known parameter and experimental data. So if the fit is good, then the model is good, then we have correct values of all these unknown parameters. And after that, if we have this model, here for example, then we can make some kind of predictions and simulation. Here we have points are our experimental data of conversion or degree of curing for 3 different temperature, for 3 different experiments. And lines, solid lines, are our model. And now we see fit is good, so our model is good. Our model can describe different temperature conditions. Here, it's okay. And now we use this model for predictions for simulation of reaction behavior at other temperature conditions. For example, here we take this model and make predictions of viscosity for different heating rate. Like here, we can put another heating rate and simulate it again with one click. We don't need to make some additional measurement. If you would like to make to calculate degree of cure for different isothermal conditions, here we have another example. We can take different temperature, for example, 10 here from 10 to 50, and we see how fast changed the degree of cure of our conversion against time. So for a lower temperature, reaction goes very slow. For high temperature, reaction goes very fast and it is less than 5 minutes. Let's see how it works just directly in the software. Go there. Here, you see here our kinetic software. We just load a data, 3 curves, which are measured with 3 different temperature conditions, 1 K per minute, 2 K per minute, and 5 K per minute. For each curve, we can make smoothing or no smoothing or just some very, very small smoothing. We can select a baseline horizontal or tangential or no any at all. Okay. For all of them, it is already done. That was data. We can switch to temperature. Now we see that the slowest heating has the lowest temperature. Then we have here the red one is 1 K per minute, orange is 2, and the green is 5. Then we can remove a slope just to have a calculation. Now pre-processing is done. If the pre-processing is done, we have data for modeling. Now we would like to make some kind of modeling. Let's go to the models, create a new model. Here we have one-step model. But now the fit of this model is not very good, is not in agreement with our experimental data. Why? Because our kinetic model must be autocatalytic reaction. Here we have some parameters, but they are still not optimized, and we can just ask software to find the optimal parameter for this model in order to have a best fit. Right now we have a best fit. It means that our one-step model can good describe all these different experiments. And it means that this model can be used for predictions and for simulation of the reaction behavior, curing behavior at another temperature conditions. Let's go there, go to dynamic. Here we can calculate put some parameters, and here we have simulation for 4 K per minute for different heating rates. And here is degree of curing. We can go to time or to temperature. We can see here is conversion, degree of cure from 0 to 1. We can see conversion rate, how intensive curing goes on, or we can see a signal. Here the signal is the viscosity. We can simulate viscosity for different dynamic conditions. We can go to isothermal conditions, for example, like here, conversion. Right now, we have predictions of curing behavior for different isothermal conditions. For very low temperature, here, -20 degrees C, we have very slow reaction, and it is still not finished after 100 minutes. And for high temperature, it is maybe 1 minute necessary for complete cure. And next one, for example, is multiple step. It's very interesting. Here we can put any temperature program. We can put initial temperature, the different number of steps, and we can put initial temperature, final temperature, and heating rate for each step. Right now I will import prepared the temperature program, which is already prepared, and make a calculation according to this. This temperature program has 2 segments. The first is heating from 0 to 30 degrees C with a heating rate 5 K per minute. And a second is isothermal, 30 at 30 degrees C, and it is 15 minutes. So the lower curve shows our temperature program. The upper curve shows our conversion. At the beginning, or degree of cure, it's the same. At the beginning, it's 0, and at the end, it is equal to 1, to 100%. We can see here a reaction rate, what is the reactivity, and where a reaction is finished. We can see the conversion. What's important, we can see here the viscosity. Viscosity goes down during heating because of normal temperature dependence of viscosity for all materials, also without any curing. Then it goes up because of our curing reaction, and then it is constant because curing is already finished and temperature is constant. That was a very, very short presentation of a very, very simple example. And now I would like to switch back to our presentation. And I think you see it here. If you would like to know a little bit more about our Kinetics Neo software, you can go to our website, kinetics.NETZSCH.com. Here we have a lot of information about features in our Kinetics software, about applications. We have some training course with step-by-step instruction how to find one or another thing, how to make a modeling, how to make predictions. For example, here is example of predictions how to make gelation and vitrification curve. You can find everything here. You can get a trial version for 30 days if you would like, and you can test the software. And software can calculate one mathematical model for a set of several measurements. Then we can use this model for simulation of degree of cure and viscosity and glass transition for any new temperature profile, and we can make optimization of curing process. Thank you. That was a short introduction. Adrian?
Yep. Thank you, Elena. So now on to the third and final part. What we're now doing is, what we're going to be doing is looking at how we can bring this together. So let's get some real rheology data we've measured on Kinexus, and let's export that. Let's put it into Kinetics Neo. And let's see what we can get. Let's see what more predictions we can get out of it. Let's get a bigger, fuller understanding of our curing material. So in this part, what we're doing, relatively simple epoxy resin, 2-part. As a rheologist, because we can look at these curing profiles, always find the explanation, the very fast setting, in this case 5 minutes. Well, we'll see what happens in 5 minutes later on. But yeah, what we'll see is, although it's fast, really the curing does take a little bit of time. But what we'll do is we'll look at some conditions to say, let's get this rheology data, let's put it into Kinetics Neo, let's model it, let's fit it, and let's see what we can get. So I'm going to talk a little bit in the first place about this rheology, what can we get from it, and then I'm going to then take over and look about, really getting into the kinetic side of this. Start off with the measurements. Well, guess what? We need our rheometer, we need our Kinexus, we need our sample, we need our disposable plates. We don't really want to stick the instrument together. And what we'll do is we'll look at this material in the first place under two different conditions. In this case, 2 different conditions are 2 different temperature ramp rates. A relatively rapid 5 degrees C a minute, and then obviously a little bit more slower, 2 degrees a minute. So what we'll do is effectively we load the material. Yes, the material is curing. Okay, yes, maybe with this material we wouldn't necessarily heat it quite as high as this. But what we want to do is a case study. It's just a model material, just to really show you real data, what we can actually do for the material. Okay. So what we do is if we look on the chart on the top left-hand corner, we'll look at the fast temperature profile first. 5 degrees a minute, you can see the green line here. Okay, we've gone from around room temperature up, in this case, to around 120 degrees C. And with this line, what we get is, and we'll initially start with looking at the complex viscosity. So as the temperature increases, and this is where we probably get the 5 minutes curing time, you can see relatively quickly there's a rapid transition until the temperature actually starts to decrease the viscosity of the material. You know, it's just basically heating up the material until we then go on and looking at approaching the final cure, relatively rapid against time, and then starts to plateau out. So if we do this again, where we just do it slightly slower, 2 degrees a minute, nice temperature profile, and again, we see an initial trend, and now we're looking at the darker line, the squares, and again, we see the quick change within, well, you know, a few minutes. Then again, as the temperature increases, we get the viscosity to go for a dip until then we approach the final cure to get then finally the plateau. So yeah, so rheology, the complex modulus, convert into complex viscosity, we see this change, okay? But then remember, when we introduce the rheology, we can also look at things like the phase angle. So now we get into a little bit more of a busier slide. This is now the same data, just presented in a different way. We now have the complex modulus in blue, okay? And the complex modulus, as I explained, is going to follow exactly the same profiles as the complex viscosity. Now, again, we've got the 2 temperature ramps in green, but this time I want to focus a little bit more on the phase angle now. Remember the phase angle, the degree of fluidity. High phase angle means liquid-like, low phase angle means solid-like. So great, you know, the overall impression is, guess what? As the material cures, it goes from very fluid-like, as you expect from adhesive. You want it to flow, you need to get out of the tube, you need to mix it, you need to get it where you want it. And then finally, of course, you want it to be quite solid-like. So you can see this material changes quite significantly. But with the phase angle, we can look in more detail about how the material changes. So the different temperature ramp rates, they don't make a huge amount of difference at the beginning. Yes, okay, there's a little bit of difference, but the different temperature ramp rates make a huge difference from when we approach the final state. And what's interesting is you can see this is a very rapid change, and then the final cure. And that's really what rheology gives you. Okay, yes, you know, we can go with the old staples, look at the complex viscosity, look at the local minimum, what's the lowest viscosity, then get through to the gel point, then get through to the cure. But don't forget the phase angle as well, which then gives you a little bit more understanding of how the material goes from a free flowing material through to a solid material. So, okay, 2 relatively simple sets of data, 5 degrees a minute, 2 degrees a minute. But now let's think, how long did that take? Okay, yeah, guess what? We're going to have to work with the material. On the rheometer, we're measuring it directly. Yes, in this example, we're using temperature to hurry things along a bit. Okay, we could have waited a lot longer and do these measurements over 24 hours. But the idea is to get some example data. And even now, this is a couple of hours worth of work once you got the measurements set up. So what happens if we want to look at different profiles? What happens if we want holds? What happens if we want heating? What happens if we want cooling? What happens if we want to do complicated profiles? Yes, you know, we could measure that, but what happens if you really want a fuller understanding? And that's where what we're going to do now is we'll take this data, transfer it, import it into Kinetics Neo, model it up, and let's see what happens. Which brings me over to my colleague Elena again to take it from here.
Here you see our measurement. Hell blue line is a temperature, heating, isothermal and cooling. And then we have shear modulus, elastic and viscous component. Firstly, we have here we have 2 steps of curing. A first step is a fast increasing of our course. Then we have a second step. Then it is a final curing. And after the first step, we see still that the viscous component is higher than the elastic component. So after first step, our glue is high viscous. It is still not solid. Then during second step, we have a gel point. And then during the cooling, we have a glass transition point. It is like a maximum in tangent delta curve. If we compare the same with DSC curve, with heat flow curve, then we have again first step, second step, and on the second heating of completely cured material, we have a glass transition the same 30 degrees C. So DSC data and rheometric data are in agreement with each other. And now let's go to make analysis very, very fast. Here, I just load our data. Here, we will switch to temperature. We will remove the slope temperature dependence. Now we have conversion. Let's make a model. Firstly, one-step model is not good for this two-step process because we have definitely two steps. Let's add a next step. Now we have two of them, but it is still not good agreement. A first step must be autocatalytic reaction. I just select the simplest autocatalytic reaction and make optimization. Right now, a software try to find best optimal parameter for both steps in order to get a best fit. So it's better, but it's still not okay. Now I will select another autocatalytic reaction with additional parameter Cn. Let's see how it works. So right now we have a first step with some additional parameter with where the order of reaction is unknown variable. Let's see what happens. Here we see a good agreement for conversion rate, for the reaction rate for first derivative. We have good agreement for conversion and for signal. Right now we have model and we can use this model for simulation. For example, we can go to time and select multiple step. We have already some prepared temperature program. I press calculate, and what do we see here? Here we have 4 steps: isothermal, heating, isothermal, and cooling. And we have for degree of conversion, we have very, very nice 2 steps. A first curing step and then a second curing step. First curing step happens during the first isotherm at lower temperature, and a second curing step happens during the heating partially and partially during the high temperature. And now we can see a signal. Signal looks like this. Here at the beginning, viscosity goes up because of curing, stay constant after the finishing of the first step, goes down because of just normal temperature dependence without any chemical reaction, then goes up because of a second step, stay constant when we have totally cured material, and then goes up because we have decreasing of a temperature. So it's very easy, and then you can do everything what you want. And now let's go to the presentation here. You saw this data, and now conclusion.
Yeah, thank you, Elena. So now really just a couple of slides just to really bring it to an end. And as you saw, what we do is, we work together. We get our rheology data, measure the material as it is, but then we can take things much, much further. We can optimize the process. We can model situations very quickly, very rapidly that would otherwise be impractical to do on a rheometer. And that's the idea, to get more understanding your materials by working together with these 2 different techniques. So just to summarize, just to put this together, what we've done is we can see with Kinexus, of course, we can measure the rheology. We'll need typically disposable plates. If you're interested in the change in time, change in temperature, even light or UV triggered, there's no problem. I'm not going to pretend to say for a minute that rheology of curing materials It's a very demanding test. And that's quite literally because these materials, they go from samples which are, well, they can be pretty low in viscosity, very low in viscosity when, you know, as we discussed, you heat them up a little bit and the viscosity decreases. But then, of course, they're designed to go solid-like, incredibly stiff. But honestly, that's a challenge that we like with Kinexus, the most sensitive rheometer on the market, with the highest torque available on a rheometer, which means we're better prepared than anybody else to be able to measure these. So yes, we can look at the cure, we can get the measurements of the minimum viscosity, the maximum fluidity, gel point, final cure, we can understand it. But we'd like to also explain, just as Elena did very nicely, that we can do kinetic analysis. We can take this rheology data, we can look at DSE data. Yes, we can look at other thermal analysis techniques to monitor the cure and allow us to model it. By modeling, what that means is now we can predict, we can optimize the systems. We can look to understand exactly the temperature profiles inside your systems. Can we look to see and reduce energy costs, for example? And that's the idea. We can put these techniques together to give you a fuller understanding of your materials. Really, you know, curing materials, this is what we do, this is what we can help you understand in a lot more detail. So really, you know, that does bring us to an end. And I'd just like to take this opportunity to, thank you very much for your time. And thank you.
Thank you, Adrian and Elena, for your nice talk. Really hands-on. We have a few questions coming in, and I think we could answer one or two. I have a question here. Do the DSC and the viscosity data give the same kinetics?
So we did, for this material, we did the following. We did measurement, DSC measurement. I create kinetic for them. We did rheological methods, and I did, again, kinetic again. So what I got, firstly, in both cases, I got two-step reactions. The activation energy per exponential factor for each step is the same for DSC and for rheometry. What was different? Different was the contribution of each step into total reaction. So for DSC, a first step produces about 60% of heat of total reaction, and the second step is only 40. And for rheological data, a first step produce less changing in the whole changing of viscosity than the second step. So that was different. A different was a contribution, but the activation energy per exponential factor and all other kinetic parameters for each individual steps were the same.
Great, thank you. Another question for you, Elena. Can the Kinetics Neo software take any data set from any instruments, or does it have to be a special data format?
No, it should not be any special data format. You can take data from any instrument and any manufacturer. So the data for Kinetics Neo is the ASCII data or text data. The text data must contain 3 columns: time, temperature, and your signal. For example, for the case of DSC, it's a heat flow. For the case of rheometry, it's, in our case, in our example, it was the viscosity, shear viscosity. So you can take any instrument.
Okay. Another question, how do I know which reaction type it is and which model I should apply? So
it's a good question. We have a couple of articles which present exactly what kind of reaction model and what kind of reaction type should be selected. So the last of them is published this year is the ICTAC recommendations for multi-step kinetic analysis. It's the International Committee for Thermal Analysis and Calorimetry. And in this article, I just wrote very, very exactly how to select it. And the topic of our webinar today is the curing. And the curing reaction is very often, or just normally, the autocatalytical reaction. So you can just select autocatalytical reaction.
Great, thank you. So I think we will wrap up now. Thank you again for joining us today. Any other questions will be answered via email. And thank you, Elena and Adrian, for your nice talk.
Thank you very much.
Thank you very much.
Have a good
Bye-bye.
day or evening wherever you are. Bye-bye.
Thanks.
Bye.